This is a picture from the Wikipedia article about the general theory of relativity, Einstein's famous theory of gravitation. The way you always hear it, the explanation goes like this. There's something called space-time, which is space and time together, and you can think of space-time like a sheet of rubber that gets curved into a dimple by the mass of a planet. That distortion causes paths to curve towards the planet, and we call that gravity. The story is correct as far as it goes, but if you're the kind of person who really likes to understand how things work, you're left with a lot of questions. Like, what does it even mean for space-time to be curved? A rubber sheet is two-dimensional, so there's room for it to curve. But space fills up all of space. Where does it curve into? When you add time to the picture, it's even more confusing. And even if you can accept the curvature, it's not really clear how it gets you gravity. I gave the example of the dimple causing a path to curve, but gravity works even on things that aren't already moving, right? What if, instead of this path, you just released a ball in space near the Earth? In real life, we know the ball falls towards the Earth, but how does the curvature explain that? The way the picture is drawn, it does look natural that the ball would just roll down the hill, but that's silly. Balls roll down hills because of gravity. Besides, there's no reason to draw the dimples pointing downwards anyway. You could create a figure with a hill instead of a valley, and the curvature would be the same. There's got to be some kind of secret sauce that makes a connection between space-time curvature and gravity. What is it? Well, part of it is that the time part of space-time is really important. For thinking about gravity, the path through space isn't really the whole picture. And the ball just sitting there isn't right either. We have to draw the diagram in space and time, like this. Each grid, each Earth, and each red ball is a different time step. But this is too much of a mess. We need some way we can think about space and time without all this clutter. What we need is a map. This is a map of part of New York City. The map is two-dimensional, but if you think about it, New York is really three-dimensional, since all the buildings have height, and there are even subways underground. If you consider the fact that the city has a past, present, and future, it's even four-dimensional. But for getting around the city, there are two dimensions that matter most, north-south and east-west. And so you can mostly ignore up, down, and past, future and just use a 2D map. We're just leaving out two of the four dimensions. So maybe we can leave out a different two dimensions. If you really care about diagramming what happens over time, maybe you can have a 2D map that just has one space and one time dimension. Let's see if we can make this work. Let's ignore time for a minute and just think about space. If you're only going to show one dimension, then basically it's as if you're just showing the contents of a tube through space, a one-dimensional cross-section. That's what this gray line here is. And here we have the Earth in space. The blue stripe just represents how far the Earth extends in one direction. We're ignoring rotation. If you like, you can imagine that north is to the right and the line goes from pole to pole. Now we can ignore the line representing all of space, but add a red rocket about to launch from some point on the Earth. Obviously way out of scale, just so you can see it. Now let's bring time into the picture. First, let's imagine a snapshot every second, and we'll let the past be towards the bottom and the future towards the top. So if you look at this, you can see that it's a 15-minute test flight. The rocket goes straight up and then comes down at the exact same spot, 15 minutes later. It's hard to look at the map without thinking that it shows the rocket moving sideways and coming down in a different spot. But you have to remind yourself that the vertical direction on the map just represents time. The only change in position is up and back down again. But anyway, there's no need to break it up into snapshots. Time runs continuously. So that map can too. The blue vertical ribbon is the Earth through time, and each horizontal slice is a different moment. Randall Munroe, in his XKCD comic strip, did some space-time maps of movie plots. He did it with time on the horizontal axis, which is actually the most common except when you're talking about relativity. But we can turn time vertical and zoom in so you can see. One thing that's different about space-time maps is that the lines you see have a preferred direction. Everything extends from the past to the future. If someone is standing still, their line goes straight up and down. If they're moving, the line tilts, and the faster they move, the more the line tilts away from vertical. You won't see a perfectly east-west line because that would represent something that took a lot of space but just appeared for a moment and then disappeared. And that's just not the sort of thing that really happens. Now, this map is sort of like a subway map, where the scale isn't important and the lines just give you a relative sense of direction and what's connected to what. But if you draw the map to scale, you can really talk about some physics. So here's a very simple map that's drawn to scale. We use seconds to measure time and light seconds to measure distance. You could use other units for time and distance, but the speed of light is a special thing in relativity, so it makes sense to use it to connect space and time. Here's the Earth from 3 seconds before noon to 4 seconds after. It doesn't move far in 7 seconds, so its line is almost vertical. And the red lines are two flashes of light going in opposite directions. Don't think of them as laser beams shooting out at a 45-degree angle. Instead, at each point in time, the flashes of light are farther from the Earth, so that when we put all the points together, they make lines that are diagonal in space and time. So, how can these maps help us think about physics? Well, let's go back to the Lord of the Rings. If this were to some kind of scale, time would have to be in weeks or months and distance in some multiple of miles. And you'd be able to tell something about their speeds from the angles of the lines. For instance, let's look at the character Treebeard. At first he's not moving. We can tell because the line goes straight up and down. And once he's heading towards Isengard, the more or less straight line says his speed isn't really changing. It looks like he's moving a long distance in not much time. Pretty impressive for a tree. And in between, he's picking up speed towards Isengard, which shows up on the graph as the line being curved. Straight lines means the speed isn't changing, and curved lines means that it is. So this is a really important point. If there is acceleration, the world line on a space-time map is curved. You may have noticed that everything we've talked about so far is really just geometry. But here's a bit of physics that you may already know. Newton's first law tells us that without a force acting on an object, there won't be any acceleration, and vice versa, of course. So, since no acceleration means the world line is straight, we have a connection between the geometry of curves and the rules about motion and force. For an example, we can't really use the Lord of the Rings map because there are always too many forces, including friction that makes things tend to come to a stop unless you keep exerting another force to keep it going. So, let's imagine we're out in deep space, where there's no air to slow us down and no measurable gravity to change our path. The red line is the space-time path of a spacecraft, relative to us. For the first 2 seconds, the spacecraft is perfectly still relative to us, so there's no force. And for the last 3 seconds, the line is straight but tilted, which means that it's moving at a constant speed relative to us. So there are also no net forces acting on it during this time. We can tell what that constant speed is. We see that the ship takes 2 seconds to move 1 light second, so it's going half a light second per second, aka half the speed of light. So between 11:59 and 59 seconds and 12 o'clock and 1 second, the speed changed from 0 to half the speed of light. That ship has pretty good pickup. But the point is, the acceleration from 0 to half the speed of light happened where the line bent. So, again, the rule is that if there are no forces acting on you, then your world line is straight. That's if space-time is flat. But what if it's curved? Realistically, true space-time isn't a ball like this, but let's just ask the question. What if the right way to map one dimension of space together with time was on a globe instead of a flat map? Then there are no straight lines. Instead, we have geodesics. A geodesic is just a fancy term for the straightest possible path on a curved surface. It's what you would get if the surface was the space between two matching layers of curved glass, and you could pull a string tight between 2 points. On a sphere, all the geodesics are great circles, like the red line here, where the center of the circle is the same as the center of the sphere. But this diagram isn't really helpful for us. Space-time isn't really a sphere, and it's not some other 2D surface sitting inside 3D space either. We need to be able to draw geodesics on flat-looking space-time maps like this one. Is there a way to talk about curvature on a map like this that makes sense even if we don't have any access to some kind of higher dimensional space to curve into? Actually, there is. Whenever you make a flat map of a curved object, the scale has to be inconsistent in different parts of the map. The top and the bottom parts here are taken from the same world map, and both horizontal lines represent 300 kilometers. The part of the map in the top had to get stretched more to flatten out the map, so it looks bigger. One way to show just how the scale changes is to cover the original curved surface with circles that are all the same size. Then, when you stretch the tight parts of the surface to flatten it out, you'll see the way the scale changes and how the circles are distorted. But once you have the scale defined on the map, you don't even need the globe anymore. For instance, you can calculate geodesics. This path may not look like the shortest path from Jacksonville, Florida to Mount Everest, but here's what it looks like if you place the scale circles right along the path. Each circle is about 400 miles, and there are 3 fewer of them along the geodesic path than along the horizontal line. The path that's straight across on the map is longer. So you can use the same method of displaying scale change and apply it to space-time maps, like our map of the Earth through time. But actually, if you want to be able to see the distortion in the space-time scale, we're going to need stronger gravity. So instead of Earth, let's have a black hole. In the middle is the singularity, which in this map looks like a line running from the bottom to the top, and the boundary is called the event horizon. Let's zoom in a little bit and add our circles to indicate the scale, like we did on the Earth. We're cheating a little bit here. In relativity, distance in time doesn't combine with distance in space the same way distance north combines with distance south, and that changes a lot of things. But it'll still give you an intuition of how the curvature of space-time leads to things falling towards the object. So imagine a rocket is hovering near a black hole. It's using its engine to keep from falling in. This means its world line is going straight up and down in this map. But this line is just like the horizontal line on this map. It's straight on the map, but not in the underlying geometry. This view is from directly over Jacksonville. So if you headed away from Jacksonville, turning neither left nor right, your path would look like a straight line from this angle, just like the blue line, for instance. So just like the red line isn't really straight on the surface of the Earth, the world line of the rocket isn't really straight in the geometry of space-time. On the other hand, once they turn off the rockets, the space-time path starts to look curved on the map. But actually, it is not curved in the geometry of space-time, or at least, it is a geodesic, the closest thing to a straight line you can have. Just like on the map of the Earth, the line bends towards the smaller circles on the map, which means that the rocket falls towards the black hole. Remember that it's actually falling straight down, only time changes as you move up in this diagram. If you start out farther from the black hole, the differences between the successive pink circles isn't as great. That means the line curves less, which is another way of saying that the acceleration from gravity is smaller. So gravity is weaker as you get farther from the black hole, just as you'd expect. So that's it. Thanks for listening.